everyone, my name is Naina and I'm from the Buddhi Academy. So today we'll start with the new chapter of Standard 11th. That is classification of elements and periodicity properties. We know there are various kinds of elements present in the earth. Now how those elements are classified, how those are placed in an order for us to use them as a convenient way, and what is their periodicity, how they are arranged, on what basis of properties they are arranged, what are their properties, what does the element have. All these things we will be seeing in this chapter. So let's start with the chapter. So classification of elements and periodicity in properties. Now in this unit we will study the historical development of the periodic table. Now it is known as modern periodic law. Okay. Now we will also learn how the periodic classification is done as a logical consequences of electronic configuration of atom. How their electronic configurations are done. Now finally we shall examine some of the periodic trends in physical and chemical properties of the element. Okay. Now these are the things that we will learn in this chapter. First thing, why do we need to classify elements? What is the need for classification of elements? So we know by now that the elements are basic units of all types of matter. Yes or no? All types of matter, they are made up of some or the other kinds of elements. For example, carbon, it is almost present in most of the compounds. Water is also a chemical compound. It carries two elements, hydrogen and oxygen. So each and everything is made up of elements. Now in 80s, okay, in 18th century, only 31 elements were known. Okay, in 18th century, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. So in 18th century it was only 31 elements which were known, but as time progressed, okay, in 1865 there was 63 elements which were discovered, which is double than the original amount of elements which were discovered in 18th century. At present we have 114 elements, okay, 114 known elements. Of them, the recently discovered elements are man-made. Okay, so this 114 elements which are there as of now, among them the ones which are recently discovered are all man-made elements. Okay, they are not natural, they are man-made. Okay, during some synthesis or some experiments these were formed. Now efforts to synthesize new elements are continuing. Now still some scientists, they are carrying out various experiments to develop or to synthesize new elements. Okay, with such large number of elements, it is very difficult to study individually the chemistry of all these elements, and there are innumerable compounds individually. So now we know there are lot of elements, right? At 114, still there is synthesis going on. So all these elements, to study each and everything, it is difficult if it is randomly arranged, right? So if it is arranged in order which will make it convenient for us to learn their properties, to learn how their compounds will be formed individually, we can learn and can get some of their properties from their arrangements also, right? So to ease out this problem, okay, to ease out the problem, because it was created by the large number of elements, how to learn them, how to study them individually, the chemistry of all these elements, to study them individually, and the number of compounds they form, to learn, to study those compounds, how they are formed, what type of compounds they are formed. So to ease out this problem, scientists searched for a systematic way to organize their knowledge by classifying the elements. So to ease out all these problems, scientists have developed a systematic way in which they will arrange all the elements and classify them. Not only that, it would rationalize known chemical facts about the elements, but even predict new ones for undertaking further study. So this will be like, if you know to arrange them, you should know some factors, right? If you know the factors, you can arrange them. So if some of them are following same factors, you can arrange them in an order, right? So it will make you more convenient to know the properties also. Genesis of periodic classification. Now, what is genesis of periodic classification? How the classification started in the initial period. Okay. Now, classification of elements into groups and development of periodic law and periodic table are the consequences of systematizing the knowledge gained by number of scientists through their observations and experiments. Now, how the classification of elements took place? It took place into groups, and the development of periodic law and periodic table. These are the consequences of systematizing the knowledge, okay, which was, or systematically arranging the knowledge which was gained by number of scientists through their observations and experiments. Now, the German chemist John Daubernier, in early 80s century, was the first to consider the idea of trends among properties of elements. Now, John Daubernier, okay, he is the first one to consider the idea of trends, okay, among the properties of elements. Now, if a element has this trends, then they will fall under this table. So he was the first one to identify the trends in properties among the elements. Now, in 1829, he noted a similarity among the physical and chemical properties of several groups of 3 elements. Now, in 1829, this John Daubernier, he noted a similarity in physical and chemical properties of some group of elements with some groups of 3 elements. Okay, he took the three elements and he found that all these 3 elements have similar physical and chemical properties, and he named that 3 element as triads. Okay, triads means 3. Now, in each case, he noticed that the middle element of each triad has an atomic weight about halfway between the atomic weights of the other 2. Now, what does this mean? For example, here there is a triad given. Okay, lithium, sodium and potassium. This is a triad which Daubernier formed. Now, what he found is that lithium and potassium, okay, if we make an arithmetic mean of lithium and potassium, now what is the atomic weight of lithium? It is 7. What is the arithmetic mean of potassium? It is 39. Divide by 2. Okay, 39 plus 7, it is 2. Okay, now when we add and divide this by 2, it was seen it almost gets the same number as the middle one. Okay, that's what he had said here. In each case, he noticed that the middle triad, okay, this is the middle triad, that is sodium. Middle triad element of each of the triads had an atomic weight, okay, it had an atomic weight about halfway between the atomic weights of the 2. Okay, halfway means if we add these 2 numbers, that is 39 and 7, how much it will become? 39, 40, 41, 42, 43, 44, 45, 46. 46 divided by 2. This is the halfway, right? Now, 2 ones are, 2 twos are, 2 threes are. So, what is the answer? It is 23. 23 is the atomic number of sodium. So, this is what Daubernier had stated. He stated that the atomic weight of the middle element in a triad is the arithmetic mean of the other two elements in the triad. Okay, similar for all these molecules. Okay, they are getting similar values. Here also, if we take, this is the middle atom. Okay, now this atomic weight of the middle atom will be the arithmetic mean of these two elements. For example, 137 plus 40, it will be 7. Okay, 3 plus 4 again 7. 177, which is divided by 2. Okay, 2 ones are 2 8s are 16. Again 1, 2 8s are 16. It will be 88.5, which is almost 88. Yes or no? So this is what Daubenheimer had given, that the middle atom, atomic weight of the middle atom will be the halfway between the atomic weights of the other two atoms in the triad. Now also the properties of the middle atom were in between those of the other two atoms. Since the atomic weight falls between, the properties also fall in between the other two atoms. Since Daubenheimer's relationship referred to as law of triads, and this is referred to as law of triads, seemed to work only for a few elements, it was dismissed as coincidence. Okay, now this law of triads had lot of drawbacks, because not all the elements can fit in a triad form. Okay, there are some elements which are not at all coming in the form of a triad, so it was considered to be a mere coincidence. It's not a property. Okay, the next reported atom. Okay, once this law of triads were eliminated, there was another attempt to classify the elements, which was made by the French geologist A.E.B. de Cancortius. Okay, in 1862, he arranged the known elements in order of increasing atomic weights and made a cylindrical table of elements to display. Now what this person had done, this French geologist, what he had done is, he had arranged all the elements in their increasing order of atomic weight. Okay, in the increasing order of their atomic weights, and made a cylindrical table of elements to display the periodic recurrency of properties. So he arranged them in an increasing order of their atomic weights. Now this also did not attract much attention, because increasing atomic orders and in a cylindrical way, there is lot of things. Now we have to also prove their properties. Just arranging them in the increasing atomic order won't make much sense to you all, right? So this is also was eliminated. Then the English chemist. Okay, there was an English chemist, John Alexander Newlands. Okay, John Alexander Newlands, in 1865, he propounded the law of octaves. Okay, he gave a law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every eighth element had properties similar to the first element. Now what this person had did, that is John Alexander Newlands, what he did is, he arranged the elements in an atomic order. Okay, increasing order of their atomic weights. Okay, as their atomic weights increases, he arranged them in an order till 8th element. Okay, element 1, element 2, 3, 4 till 8, he had arranged them in their increasing order. Once the 8th element is written, the 9th element, he wrote it down. Okay, so what he made is that the elements in an increasing order of their atomic weights, and noted that every 8th element, till 7 he wrote on the top. Every 8th element he wrote it below the first element. Okay, every 8th element he wrote it below the first element, and he mentioned that every 8th element in this order. Okay, when you write them in their increasing weights, okay, increasing atomic weights, when we write them, every 8th element will have same property to the first element. Okay, now the relationship was just like every 8th note that resembles the first in octaves of music. So he compared it with the musical notes. Okay, what musical notes we follow? We follow sa re ga ma pa dha ni sa, no? So it starts with sa, ends with sa. So same thing he followed for the law of octaves. Okay, every 8th element is similar to the first element. That is what he had said. Now, Newland's law of octaves seemed to be true only for elements up to calcium. So it was proved to be true. Okay, Newland's law, whatever he said, कि every 8th element has similar property to the first element, was true, but it was only applicable till calcium. After calcium, it seems to be not the same case. Okay, now although his idea was not widely accepted at that time, he for his work was later awarded by Davy Medal in 1887 by the Royal Society of London. Even though his work was not considered to be great, but his idea of putting them in such a way, and it was also true till calcium, right, till element calcium, this was proven to be true. So for that he was awarded Davy Medal in 1887 by the Royal Society of London. Now the periodic law, as we know it today, owes its development to a Russian chemist, Dmitry Mendeleev, and the German chemist Lothar Meyer. Okay, now these are the scientists who worked on them. Okay, starting they paved the way for the new periodic law. Okay, now these were the ones which were initially proven, which led to the new periodic law, or the periodic law that we follow now. Okay, the periodic law that we follow now was greatly, or it owes its development, it was basically developed by a Russian and a German chemist. Okay, Russian chemist Dmitry Mendeleev and the German chemist Lothar Meyer. These were the two persons who had made most of their contributions to the periodic law. Now, working independently, they didn't work together. Okay, they worked independently. Both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. Now what both of them stated? They stated that when you arrange the elements in their increasing order of atomic weights, okay, in the increasing order of their atomic weights, similarities appear in physical and chemical properties at regular intervals. It is not like it will appear at a certain point and then again it will appear after 10 elements, then after 30 elements. It's not like that. Okay, they stated that if we arrange the elements in their increasing atomic weights, okay, at regular intervals means if after 10 elements, okay, after 10 elements, the remaining 10 elements, when we arrange them, okay, like 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, these are the 10 elements, okay, which I arranged them in their increasing atomic weights. Now when I arrange the second row, okay, I'll start with 11, 12, 13, 14, 15, 16, 17, 18, 19 and 20. So at regular intervals, it is seen to have a similar physical and chemical properties, okay, at regular intervals. So if I take the interval to be 5, after every 5 elements, it was seen that the properties of those elements seem to be similar. Okay, this is what Dmitry and Lothar had said. Now Lothar Meyer plotted the physical properties such as atomic volume, melting point and boiling point against atomic weights and obtained a periodically repeated pattern. Now what did Lothar Meyer worked on? He basically worked on the physical properties of those elements. Physical properties like their atomic volume, melting point, boiling point against the atomic weight, and he obtained a periodically repeated pattern. Okay, he obtained a repeated pattern that every after 5 elements the pattern is repeated. Okay, unlike Newlands, okay, Lothar Meyer observed a change in length of that repeating pattern. Now, Newlands, what he did, he only did till 8th element. He said that after every 8th element, when we arrange them in the increasing order, every 8th element has a similar property with the first element. What about the other elements? Do they have a similarity? That Newlands didn't do. Okay, but Lothar Meyer, he observed a change in the length of the repeating pattern. How it is repeat? At what element it is repeat? What about the other elements? Okay, so he worked on those things. He observed those changes. By 1868, Lothar Meyer had developed a table of the elements that closely resembles the modern periodic table. However, his work was not published until after the work of Dmitri Mendeleev, the scientist who is generally credited with the development of modern periodic table. Now, Lothar Meyer, he developed the table. Okay, under his observations, he developed a table. Okay, which resembles very closely to a modern periodic table which we follow now. Okay, the table that Lothar Meyer had given, it resembles the table, modern periodic table. However, his work was not published until after the work of Dmitri Mendeleev was completed. Okay, the work which Dmitri Mendeleev had done, after his work was completed, okay, then after that only his work was published, and Dmitri Mendeleev, he is credited basically for the development of the modern periodic table. Okay, while Daubigny initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. Okay, even though this periodic classification or the study of periodic relationship was started by Daubigny, Mendeleev was the one who is responsible for publishing that periodic law. Okay, for the first time. Now, what does his law states? The law states that the properties of the elements are a periodic function of their atomic weights. So, whatever properties that elements have, okay, is a periodic function of their atomic weights. It is due to their atomic weights. Okay. Now, Mendeleev, he arranged elements in horizontal rows and vertical columns of a table in order of their increasing atomic weights in such a way that the elements with similar properties occupied the vertical column of or group. Okay. Now, how Mendeleev had made his table? He arranged the elements horizontally. Okay. He arranged the elements in a horizontal rows and in vertical columns. Okay. He arranged the elements in an horizontal row and their properties in a vertical column. Okay. Now, of their increasing atomic weights in such a way that the elements with similar properties occupied same vertical column or group. So, he arranged them in such a way that the elements which had same properties, okay, they were arranged in same vertical column, or they came under the same vertical columns or groups. Now, Mendeleev's system of classifying elements was more elaborate than that of Lothar Meyer's. Even though Lothar Meyer had prepared a table, but Mendeleev, the table or the classification of elements which Mendeleev had given, it is more elaborate, it is more precise than Lothar Meyer's table. Now, he fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. Now, Mendeleev, he recognized the significance, importance of the periodicity, why it is important to arrange them in an order, that too with similar properties, why it is a need. So, he understood the importance of that, and he used a broader range of physical and chemical properties. He included almost all the physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compound formed by the elements. So basically what he did is he relied on the similarities of empirical formulas. Empirical formulas means the formula, the compound which these elements form. Okay, if it is PCl5, okay, if it forms SCl5, CCl5, okay, these are the empirical formulas. If these molecules are forming this kind of compounds, then they have a similar properties. Got it? This is just an example. Okay, so this is how Mendeleev had made, or this is on this basis was Mendeleev relied to form his or classify its elements. Now, he realized that some of the elements did not fit in with his scheme of classification if the order of atomic weight was strictly followed. Okay, if he followed the order of atomic weights, it was seen that some of the elements, they doesn't follow the rule, or they doesn't follow the characteristic which he has, or the classification which he has organized. Okay, so he ignored the order of atomic weights, thinking that the atomic measurements might be incorrect, and placed the elements with similar properties together. So what he did was, if he had gone with atomic weights, at certain points it was seen that these atomic weights and their properties are not matching, or it is not falling under his classification criteria. So he ignored the atomic weights. Okay, he ignored the atomic weights and he placed the elements on the basis of their properties. If they have a similar properties, they are placed there. Whatever their atomic weights may be, if they are having similar properties, they will fall under this group. Okay, because those atomic weights, there is a possibility that they might be incorrect. Okay, there can be a calculation error which can occur. So the weights might be incorrect. That's why it is not falling under the properties, right? So because of this reason, he ignored the atomic weights and he placed the elements on the basis of their similar properties. Okay. Now, for example, iodine. Okay, iodine with lower atomic weight than that of tellurium was placed in group 7 along with fluorine, chlorine and bromine because of similarities in properties. So iodine, okay, it has a lower atomic weight, okay, than that of tellurium. Okay, iodine and tellurium was present in group 6. Now it is present in group 6. Iodine is present in group 7. Okay, iodine being lower in its atomic weight than tellurium. Usually in place of iodine, if according to atomic weights, if we place the molecules, okay, in the elements according to the atomic weights, if we place that elements in place of iodine, it should be tellurium. Okay, but the properties of tellurium and iodine is completely different. Group 7 molecules or elements like fluorine, chlorine and bromine, they showed a similar property with iodine. Hence, iodine was placed in group 7. Being the lower or having the lowest atomic weight, iodine was placed in the group 7 along with the fluorine, chlorine and bromine because they showed a similarity in properties. Okay. Now, at the same time, keeping his primary aim of arranging the elements of similar properties in the same group, he proposed that some of the elements were still undiscovered and therefore left several gaps in the table. So what he did was, even though he arranged the elements in a table with their similar properties, he left a gap in the table, and for that gap he mentioned that there are still some elements which are undiscovered, and those undiscovered elements will have same properties like this. So those elements will be placed here. Okay, so you can now think that he was such a great person. So even before the discovery of elements, he left a place for those elements. Okay. Now, for example, both gallium and germanium were unknown at that time. Mendeleev published his periodic table. He left gap under aluminium and a gap under silicon and called these elements eka aluminium and eka silicon. Now you can see here it is very interesting. Before, okay, Mendeleev published his periodic table. Okay, he left a gap between aluminium, or he left a gap under aluminium and silicon. Okay, under aluminium and silicon he left a gap, and at that gap he written it as eka aluminium and eka silicon. Okay, later gallium and germanium were discovered. These are the two elements which were discovered after the publication of Mendeleev's periodic table. Okay, both gallium and germanium had similar properties, which was written by Mendeleev on his periodic table as eka aluminium and eka silicon respectively. So you can know he predicted that there will be some elements which will be showing the properties of this element which are not yet discovered. So Mendeleev predicted not only the existence of gallium and germanium but also described some of their general physical properties. He not only predicted that there will be some elements which are present and will have these properties, he also gave their general physical properties also. Okay, these elements were discovered later. So Mendeleev, he had done a great job in its periodicity. Okay, some of the properties predicted by Mendeleev of these elements and those found experimentally are listed below. So whatever the results which Mendeleev had predicted, okay, and the ones which were experimentally found after the discovery of those elements were listed here. So the property of eka aluminium, which was predicted by Mendeleev, and gallium, which was found. Okay, so the atomic weight Mendeleev predicted was 68, gallium ka it is 70. Now the density of that element predicted was 5.9, found was 5.94. Melting point was found to be low. Formula is E2O3, E for eka, okay, E2O3. Now formula for gallium is Ga2O3. Now for chlorine or for chloride it is ECl3, for gallium it is JCl3. So you can see that some of the properties which Mendeleev had predicted, okay, they are exactly the same as what we had got after the discovery of those elements. Now the boldness of Mendeleev's quantitative prediction and their eventual success made him and his periodic table famous. So the boldness, with the confidence he stated that the quantitative prediction, that this will be the density, this will be the atomic weight, this can be the oxide it will form, this will be the chloride it will form. So with that confidence, with that boldness, he predicted the quantitative things and their eventual success, and it was found to be true, right? So the eventual success made him and his periodic table very famous. Okay, now here they have given the periodic table of Mendeleev. Okay, so this is the first this is the periodic system of elements in groups and series. So this is the series and these are the groups of elements. So now you can see he had arranged them in such a way that everything is under their properties. Okay, now you can see there is difference in their atomic weights. It should be 4, 19.9, 38, 81.8, right? But what Mendeleev had did is he arranged them in such a way that their properties remaining same. Now you can see helium, neon, argon, krypton, xenon, we call them as noble gas, right? So they come under one table. Now fluorine, chlorine, bromine, iodine, these are our halogens. They also fall under one group. Yes or no? So he had arranged them in such a way that everything is falling under one group. Here, this is a Transition element, first series of transition elements, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. There is copper, which is still not found at time. Okay, copper, and there is zinc. So he was such a brilliant person. He arranged them in such a way that their properties remained same. Okay. Next is the modern periodic law and the present form of the periodic table. Okay. Now we must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. However, the beginning of the 20th century witnessed profound developments in theories about subatomic particles. So when Mendeleev had developed his periodic table, at that time none of them knew the internal structure of an atom, how an atom looked. Okay, what is the structure of the atom? No one had known this. However, the beginning of 20th century, okay, as 20th century began, at that time, okay, there was development in the structure of atom, and there were various theories which stated the subatomic particles. Now, in 1913, the English physicist Henry Moseley observed regularities in characteristic X-ray spectra of elements. Okay, Henry Moseley, he is the one who observed the X-ray spectra of elements. Now, a plot of delta V, that is the frequency of X-ray emitted against the atomic number, that is Z, gave a straight line and not the plot of delta V versus atomic mass. So when this was observed, okay, he observed a regularity in the characteristic of X-ray spectra. What he did, he plot a graph of frequency which was emitted by the X-rays against the atomic number of that elements. Okay, and he found a straight line. Now, he thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. So after that, he was the one who stated that compared to atomic mass, atomic number is the more fundamental property of an element. It is the basic of an element. Now, Mendeleev's periodic law therefore accordingly modified. So on this basis, Mendeleev's periodic law was modified accordingly. Now this is known as modern periodic law. Now this is what the modern periodic law was. It was a modified version of Mendeleev's periodic law according to the theory which was given by Henry Moseley. Okay. Now what is it? The physical and chemical properties of the elements are periodic functions of their atomic numbers. Now Mendeleev had said that it is periodic function of their atomic weights, right? Now we know it is not because of their atomic weights, it is because of their atomic number. So it is accordingly altered as the physical and chemical properties of the element are periodic functions of their atomic number. Okay, we have changed the atomic weight to atomic number. The periodic law revealed important analogies among 94 naturally occurring elements. Okay. Now, periodic law, it revealed analogies. Okay, analogies means similarities among the 94 naturally occurring elements. Now, neptunium and plutonium, like actinium and protactinium, are also found in pitch blende and ore of uranium. Okay, these are the things which are found in an ore of uranium. Now, it stimulated renewed interest in inorganic chemistry and has carried into the present with the creation of artificially produced short-lived elements. So this is what stimulated the interest in inorganic chemistry, and they started to develop and artificially produce short-lived elements. Now, you may call that the atomic number is equal to the nuclear charge, that is number of protons. We know atomic number is equal to number of protons or number of electrons, because both are equal in a neutral atom. Now, it is then easy to visualize the significance of quantum numbers and electronic configuration in periodicity of elements. Now it is easy to visualize the quantum numbers, right, and the electronic configuration in periodicity of elements, because their atomic number will give you the number of electrons which are present or the number of protons which are present. Now, in fact, it is now recognized that the periodic law is essentially the consequence of periodic variations in electronic configuration. Okay, now it is stated that the periodic law is the consequence of periodic variation in electronic configuration. Periodic law was the one which changed the variation, or which showed the variations in the electronic configuration, which is indeed determine the physical and chemical properties of the elements and their compounds. So this is also important to identify the physical and chemical properties of the elements and their compounds. Now, numerous forms of periodic table have been devised from time to time. Okay, there were various periodic tables which were devised time to time, which were deleted or which had lot of limitations or drawbacks, so new ones were put forth. So after various consultations, now we have that modern periodic table which we follow. Now, some forms emphasizes chemical reactions and valences, whereas others stress the electronic configuration of elements. Now, some of those, okay, they emphasize or they stress mainly on chemical reactions and its valences, whereas others they stress on electronic configuration of the elements. Now, modern version, the so-called long form of the periodic table of elements, is the most convenient and widely used. Okay, the periodic table which we use now, okay, modern version, it is called as long form of the periodic table. Okay, now the horizontal rows which Mendeleev called series are called periods. Okay, the horizontal row which Mendeleev had made and he called them rows, series, now we call them as periods, and the vertical columns are groups. Okay, now we have periods and groups. The elements having similar outer electronic configuration in their atoms are arranged in vertical columns referred to as groups or families. Okay, so elements which are having similar outer electronic configuration, okay, the outer orbit having same number of elements or electrons. Okay, for example, fluorine, chlorine, bromine and iodine. All these four molecules on the outer shell, they have only 1 electrons each. Okay, all four of them have one electron each in their outer electronic configuration. Okay, so they fall under one category. Okay, they fall under one vertical column, and this column is referred to as groups or families. Now, according to the recommendation of International Union of Pure and Applied Chemistry, that is IUPAC, okay, International Union of Pure and Applied Chemistry, this is the section which is involved in naming. Okay, they name a newly found element. The groups are numbered from 1 to 8. So they have numbered the groups from 1 to 18, replacing the older notation group, that is 1A. Okay, that Roman number notation which was initially given by the Mendeleev, that was removed and it was numbered from 1 to 18. Now, there are altogether 7 periods. The period number corresponds to the highest principal quantum number n of the element in the period. Now, altogether there are 7 periods. Okay. Now, period number correspond to the highest principal quantum number of the elements in that period. Now, the first period contains 2 elements. The subsequent period consists of 8, 18, 18 and 32 elements respectively. Okay. Now, the 7th period is incomplete, and like the 6th period would have a theoretical maximum on the basis of the quantum numbers of 32 elements. Now, in this form, the periodic table of 14 elements of both 6th and 7th periods, that is lanthanoids and actinoids respectively, are placed in a separate panel at the bottom. So lanthanoids and actinoids, they are still incomplete, or the properties and studies are still going on. So they are placed separately at the bottom of the panel, and they are named as F block elements. So here you can see the modern periodic table. Okay, so here you can see there are periods, total 7 periods and 18 groups, each group having the elements arranged in their order. Okay, this is the lanthanide and actinide series, which are arranged which are kept separately. Okay, so this is what we will have today. This is all for today's video. I hope you all have understood the things. Thank you for watching my video. Please do like, share and subscribe to our channel.